Well, good afternoon. This is April 6th, as it says here on the sheet. About to run out of paper on this pad. I'm going to mark off the last couple pages so that we're set to go, and we may have to stop for a second and get a new pad. One thing, you have a new schedule. I call it Schedule 2. This was to accommodate the fact that I did an extra lecture on state estimation. Originally thought 1, then 2, then 3. That's a big, complex topic. The next topic that we're going to do is scheduled for 1, and I am definitely only going to spend 1 lecture on it. And that is automatic generation control. This is the official, and of course it's abbreviated AGC. This is the official IEEE. You may see literature where you see the term load frequency control. Or LFC. This was the older nomenclature. Some, perfectly obnoxious wise guy probably pointed out the fact that we don't control the frequency. We control the generation in order to keep the frequency where we want it. And so, on that basis, they changed the name to automatic generation control, which is a little more accurate. But there are several things that why do we need AGC? There's several things that it does. It's a control system, primarily keep the frequency at 60 hertz in the United States and other parts of the world. About half of Japan is 60 hertz. The other half is 50. Much of the world is 50. Much of it is 60. If you trace your electric power system back to the British Commonwealth countries, probably you're at 50. The British and the Europeans adopted 50 hertz. The Americans adopted 60 hertz. I have a little write-up that I'm going to put in with the information on this section, on this problem session, about, because students ask, well, where'd 60 come from? And unfortunately, there's not a simple answer, but there is a nice paper. The paper actually is 99 years old. It's dated 1918, and somebody wrote a paper all about how did we get to 60 hertz. And it's not a simple 1 or 2 step explanation. But we need to keep the frequency approximately at 60 because in the first place, the large generators are designed to operate at 60. You get them too far from 60, they get into trouble with overheating one place or the other, or other difficulties in the turbines and things like that. Things operate, they want to operate where they're designed for. Motors, the same way. If the frequency is off, motors won't operate properly and they will shut down. So we want to keep them at 60. Now, it used to be that that they worried a very great deal about how how close they were to 60, and they would integrate the error, which turns out to be how much a clock that's synchronized to the 60 hertz system, how much time error. If you integrate the frequency error, you get the time error. And they'd always want to, they have standards that want to keep the time error down to a certain small number of seconds or something like that per day. Today we don't depend on the power system that much at all for time. I have a clock. I have a clock in my office at the university. I also have one at home that is it's powered off the grid, but it has a battery backup. It has a quartz crystal that keeps it fairly accurate, but it also has a radio receiver that picks up a signal from the Institute of Standards and Technology, or National Institute of Standards and Technology. So NIST puts out a signal that says this is time, and they have something that ticks away, and they keep that by they used to do it by celestial observations. Now I understand it's by certain vibration of a certain type of atom. In any event, they are the keepers of the time standard, and you can receive that signal in a little clock. And the really neat thing about that little clock is when daylight savings changes and you're supposed to either jump ahead or backward in 1 hour, it does it automatically. So that's a very nice feature on those clocks. So you don't really need the grid anymore for time keeping. Nonetheless, you do for the sake of the machinery. Okay. The AGC is to control the generators to their economic set point. In other words, we run economic dispatch, and it says this generator should be putting out exactly this much to be the most economic generator, and the control system that keeps the generator at that point is the AGC. So it's the means of they don't call up the plant and have the guy dial it in. That won't work. It's done with a feedback control system that comes from measuring the plant output all the way back to the AGC, and then all the way back into the what we call the speed governor on the plant. AGC. Now remember, AGC is the centralized control, and it keeps transactions. That means power transactions between buyers and sellers on schedule. That's very important. If you're buying 100 megawatts and your neighbor's supposed to be selling you 100, you don't want faulty equipment to have it turn out that you're only getting 98. And you're going to buy this for many hours. So, that's 2 megawatt error, let's say for 10 hours. That's 20 megawatt hours. That gets to be a little bit of money. And you want that contract to be met very closely. And AGC, that's another job that AGC fulfills. Okay. There's two basic parts to this. Two basic parts, and we have a control center, and it has communication lines or circuits out to generator plants. So that here's a generator. You might have a hydro turbine. They get into this as well. And at the control center is where the program, and it's a program inside a digital computer. The original AGC programs or LFC programs were actually performed on an analog computer. I have a feeling here that when I say analog computer, people look at me and think, what's that? You can build a computer with operational amplifiers that do integration, and you set up all the differential equations with feedback loops on it, and it'll solve the differential equations instantaneously, and you can have a control system set up on an analog computer. That is gone away now. Almost completely. It's always done by sampling and getting digital input and running a digital computer program where you have much more flexibility. And then down at the plants, inside the plant, we have, let's take a steam plant. We have a steam generator here. Here's a turbine. Here's a shaft. Here's a generator. Here we have the electrical output. But the shaft is rotating. Okay, it is rotating, and here's the steam coming in, and there's a valve. So just draw. Here's a valve, and we're going to show you various drawings later. But we measure the rotational speed. We measure the rotational speed, and we have a omega reference. Here's omega, the speed of the shaft. How do you measure the speed on the shaft? With digital means, you place very, very accurately ground small notches on the shaft, and you put a light on it, and then a photocell picking it up, and the photocell gets what's equivalent to a square wave, or it gets a blip, blip, blip every time a mark goes by, and you accurately measure digital measurement of the time between the pulses, and average that can be translated depending on the diameter of the shaft, how far, how fast it's rotating. So you now have delta omega, and what you want to do is you want to have a control signal, and the control signal will open, close. And so this is called just a speed governor. Speed governor. You have one on your car. If you have cruise control on your car, you set the speed, and as you come to a hill, the car slows down, the motor. There's a detection of the speed, and they open up the carburetor, feed more gas to the engine, and so forth. This is a speed governor. Now, and so there's a speed governor here, and then there's some central unit up here that's doing AGC. Okay, let's go into some of the slides. I'm going to jump back and forth between the slides that you had off of CUSP. I have a wonderful excuse me. I seem to have we Americans have an expression. We say we have a frog in our throat. I don't know where that came from, but anyway, I have a frog. I have a friend of mine who, let me make sure we can see this. Bob Green works for a power company. He worked for several manufacturers, and I crossed paths with him many years ago, many times. And he is he's a specialist in low frequency control, And he has done just a wonderful job of putting together the story of governor. Remember I said we have a speed governor and we have AGC. And so he does a nice job of this. And so I thought I would just go through this. And I will give you this set of slides. Now, I could probably pull the camera back up so that this thing I didn't have to move it. But unfortunately, I don't want to try that while we're on class because I might get it wrong and it would take us too much time. 2 generators with governors having output feedback. So here's our loads. Okay, we have 2 generators and they're feeding electric power here. So here's P1 and P2, and this is the consumption of power over there, and he shows a little switch or a breaker that can close in and cause a jump in the load. And each generator has a turbine that's spinning the generator. Notice that and this is mechanical here. This is electrical. We're back to mechanical here. Now, later on, in fact, on the next slide, he talks about what is this thing down here. And one of the things I love about this is that this is when I took the course. This is what used to be called a Watt type governor, after James Watt, who realized that he needed to be able to control the speed of a steam pump, steam engine driving a pump. The first steam engines were used to run pumps to pull water out of coal mines. And so he has something up here that's going to open and close, and this is a valve. So let's just put that up here. Here's a valve. The valve can be used to let steam in or to let water in if it's a hydroelectric system. And you have it goes up. We'll note that it goes up to open and down to close. Now, what he shows over here is basically what these are. There's 2. The better way to picture it is a shaft like this, and a sleeve that is fixed, and another sleeve that can move up and down. And then out here we have so this. And these are weights, usually in the shape. I doubt if they would be necessarily in the shape of a ball, but apparently they were initially. And this shaft is turning, okay, and that shaft, so it means that this whole thing is turning. And you can see that if it goes up and down faster, the fly balls go out. And so it was called the fly ball governor. So that they go out, and then this thing goes up. That thing goes up, and there has to be a spring holding these things, so that as if it slows down, then they go back in, and this thing would go back down. So again, this would go up if higher speed, and it would go down for lower speed. Well, that's what he's showing here. Is he's showing that thing? I think that my diagram would have been a little bit better, but this does show you. Notice, if you will, that there's a fixed fulcrum over here. Later on, we're gonna change that. So this is a lever in here, and it moves up and down the spring goes up and down. But the most important thing is that if this goes up and down, it moves a valve. And there's a he calls it high pressure oil supply down here. Well, that's just simply a hydraulic system, or you know, the kind of hydraulics that you'd have in a piece of heavy construction equipment. And it either goes, if it goes one direction, it pushes over here and it moves, so it can move this thing up and down. So if the speed goes up, you want to close this valve. So you want the thing to go down, so you want this thing to go upward. Now again, you've got a fixed fulcrum here. So if you want, let's see, if you want it to go up, then you want this thing to come down. That's why he's showing this, and this is coming down, and this is a fixed. So if that's going to come down, then it's just going to come down like that, and this comes down, and that's the. So the idea being is that the speed of the shaft on the motor, when it gets under load, it slows down. When the load goes away, it speeds up, and that translates into a moving of the valve, opening and closing. That was the first speed governor. I don't know for sure, but I'm betting that steam engines used in permanent facilities such as water pumping, such as factories, anything like that used a steam engine to drive things, would use this flyball governor well up into the 1900s, because there was no electronics. Eventually, you could probably do it all with well, it would be done with mechanical controls and so forth. But you had to have something to translate speed to movement. Centrifugal force is perfect. How they actually looked, I don't know. Nowadays, it's done again with digital computers, digital control systems. A large generator system has a digital control system around it. So here's the response without feedback when you have a change in the requirement for power. So when you have a delta P, you want to get more power out, and as soon as you want more power, you put more load on the motor, and the frequency drops. The frequency drops because you're actually stealing energy from the rotating kinetic energy of the generator. The frequency drops. The motor slows down, you're getting more power out of it, and now the governor takes over and brings you back, but not to zero, not back to 60 hertz. And the frequency, so you get more power, the frequency goes down, comes back, and there's a slight deviation. We're going to talk, that's important to note. It does not reset it to zero yet. So there's a characteristic to the governor called, you can call it the speed characteristic. That's a nice word. The nomenclature that got used is the term droop. Call it slant, whatever you will. It just means the fact that the characteristic runs like this, and it simply says that the characteristic, the droop is called R, okay, and R is equal to the change in frequency, let's use a small f, the change in frequency to the change in power. It's usually expressed as 1 over R is delta P over delta F. So it's the ratio of frequency change to power change on that governor. So that's the speed characteristic right there, is that slope. And we'll see Now, what happens when we have multiple governors attached to the generator? I will let you go through these calculations. As I said, I will give you a copy of this presentation. So how do governors with the steady state speed characteristic interact when there are multiple generators in a power system? This is what's very, very important. It's very important. And what determines the steady state frequency of the system? How do we get that to go to where we want, to 60? And so here's an example. He's got an example. He's got three generators. He's got a load, and he says he's supplying 360 megawatts here. He's got different droop characteristics, or this is 1, 2, and 3. He's got different droop characteristics. So there they are here. How many megawatts per hertz, if you will, in there? But it's usually expressed as a percentage. Much of the time, you will see this as a percentage on the base, where the base is the capacity of the generating unit. So you have to convert the numbers to get them to a common base in order to do the problem. Now, the genius of the let me come back to my written part here so I can write this in red. The characteristic of an AC power system which makes it work is the fact that frequency is the same everywhere. The same everywhere. The genius, and I don't think when they built it that they said, well, let's do it this way. We're going to have an AC system and the frequency will be the same everywhere. I think they went to AC, of course. You know, DC lost the battle. Westinghouse won out with his DC, I should say Westinghouse and Tesla, who was the genius behind three-phase AC. We went to AC so that we could change voltage levels in transformers. And therein lies the when we started that defined why we went to AC. Why we went to AC? We could we could come out of the generator at whatever, I don't know what they were initially, the generators of the 100 years ago, but they probably weren't anywhere close. So let's say they were 10,000 volts. Then they wanted to boost it up to, let's say, 220,000 volts. Well, the only way you can boost it is with a transformer. Once you do that, you can send it for hundreds of miles. Then you can reduce the voltage back down again. By the way, by going up through transformer and down through another transformer, you reduce the current through that high voltage part of it, and thereby the voltage drop is much less, and so you've helped the voltage regulation of the system. You've reduced the losses, because the losses, of course, are proportional to the square of the current. So if you reduce the current by 10, the losses go down by 100. So you get a tremendous advantage to AC. But the other part of it that sort of came along for a great advantage is the frequency is a signal that I can look at, and it's the same. The signal stays the same everywhere. It's as if I ran a communications line to every control center and every generator all over the system to tell it what the load balance was. So once again, I'll put this in blue here. Frequency tells us if load and generation are balanced. Meaning load equals generation. If load doesn't equal generation, the system is slowing down or speeding up. And frequency is changing. And we have a signal that's broadcast virtually instantaneously all over the system that tells us what that load balance is like. And if the frequency is going down, everybody on the system knows that there's too much load and not enough generation. If the frequency is going up, it's the opposite. There's too much generation, not enough load. So this means that we can use that frequency as the signal at every generator as to whether the generator should go up or down in its output. Okay, up or down in its output. So that this allows us to control the generation very accurately. Now, if you're operating a motor pump, I suppose they sooner or later got into the situation where they somehow had two motors and the shaft. They were probably directly connected to the pump, but maybe they had two motors mechanically connected to each other through gearing, I don't know, and controlling a pump. And now the pump needed more energy in because the water level changed, or they wanted to pump faster. And how does that allocate? How do you control the speed of the pump when you have two motors driving it? But that problem definitely comes up with electricity. We don't build one single generator and just distribute it to everybody. Now, you could initially, when you just had a power company was a company that operated in one small town or in one square, 4 to 10 square blocks of a city. And outside that, it was a different generator, and they aren't connected. But once you started connecting the generators, you have to have some way to control them, and that's the AGC. But first of all, the speed governors. Okay, so now, and Bob Green developed. I wrote him an email today, and I've had some contact with him the last few years. I said, Bob, where's that spreadsheet? I can't find it on my hard drive. I used to have this. This is actually a spreadsheet. And the nice thing is you can go in and you can change the load, and you can see things happen on the diagram here. It actually moves the lines. It's all in color. Well, you'll see that when you get the PowerPoint. It's beautiful. It's just beautiful. But here, what he's showing us is 3 generators, and you can see I've got one generator at 80. So here's the generation: 80, 120. Of course, that sums to 200 and 160. So that all adds up to 360. So I've got one of them at 80, one of them at 120, and one of them, the third one, at 160. And everything is operating. Here's frequency is on this axis, and this is just something showing the output. Notice, if you will, that one generator has a very steep characteristic, and then this generator over here has a different droop, a different slope to it, a different droop characteristic. This one, if there's a change in frequency, so if suddenly the frequency changes, this one will get a large change in generation. This one won't get much change in generation. Typically, this would be a smaller generator, and that's what he's got up here. He says this is a 300 megawatt generator, here's a 450, and here's a 600 megawatt generator. So for a larger generator, the change in frequency will cause the valve to move, and you'll get a larger change in megawatt output. So it's all at steady state. It's at 60 hertz, and now all of a sudden the load changes to 367. Okay, and he picked those numbers. Bob is like me, picked the numbers so that he could teach you, but you didn't have to worry about decimal points. So this one goes to 81, so that's an extra 1 megawatt. This one goes to 122, that's an extra 2. So we've picked up 3, 1 here, and 2 more here is 3. And this one goes up to 164, it's picked up 4. There's the pickup of 7. 1 extra here, 2 extra here, and 4 extra there. And see what happened? See, the frequency drops to 59.95. Frequency on a power system doesn't go up and down by very much. It doesn't go up and down by very much. You're worried about small fractions of a cycle per second or a hertz. So the frequency drops just a little bit. So this is the lower, the frequency goes down here, and you'll notice that if we draw triangles here and here and here, here I get 1, here I get 2, and here I get 4. So this is the plus 1 megawatt, plus 2 megawatt, and plus 4 megawatt. So that's what this thing, and so they're all intersecting along that line. So now I have 167, and the frequency would come down to that point, and if the load had increased by 7 megawatts, everything would be happy, except the frequency would not be at 60. The governors would have moved the generation up, but it would not have restored the frequency back to 60. That's important. It requires an additional control loop, so to speak. If it went to 374, so now we've increased by 14, we pick up 2 here, we pick up 4 here, that's 6, and we pick up 8 here. So it's just different, and you can see that the frequency has dropped much further to accommodate a larger load increase. So once again, the load goes up suddenly, the generators will go up. Now, the most common event on the power system that's going to cause large shifts in frequency are not load changes. Most loads are small, and they're all part of a random set of load, people turning on things, factories turning things on and off. When you get a big change is when you drop a generator. Suddenly something goes wrong in the power plant, and the control system scrambles and shuts the generator down, and the first thing they do is open the circuit breakers on the generator itself. Now you've gone from, let's say, 500 megawatts into the grid to nothing at that location. So now you're suddenly less 500 megawatts. Well, that you could say it looks like an increase of 500 megawatts in load, but it's just you can't get a load. You can't get 500 megawatts of load to change like that all of a sudden. I once heard a radio program where they were. Is a science fiction program where they were talking about everybody in the United States was going to synchronize to some radio station and turn on their lights, turn off their lights, turn on their lights, in order to see if they could see the lights going on and off in some Earth satellite or some rocket above the Earth. Years later, when I was learning the stuff about AGC, it occurred to me that turning an enormous, let's say millions of lights on and off, probably would have rendered the system unstable after only a few cycles, and the power system would have shut down because of trying to turn load on and then off and on and off. These AGC systems, so we would not have been able to cope with that. But we don't have that. It's not doing that. It's randomly going on and off. 381, and it's just, he's just got several examples here, picking up 3, 6 is 9, and what did he pick up? 21. So here he picked up 6, here he picked up 3, that's 9, and here he picked up 12. Okay. Same thing. We get these excursions. The frequency goes down and the generation goes up. Here I can draw the generation going up. Okay. If the system frequency reaches steady state at a value that causes the sum of the online generator output in megawatts to equal the system load, then the frequency is gonna stabilize. Okay. So that when we have an increase in load, the system will start to drop in frequency until the load equals the generation, until things are balanced. Okay, so I should have gone back before and said, well, you've got a frequency signal, but it doesn't. The fact that the frequency signal says the frequency is lower than 60, it's probably got too much load, but only if the frequency is actually changing in a negative direction. Because once the new load is balanced by new generation, there's nothing to send the frequency back to 60, but it'll stop moving. Okay. So it can be a lower frequency, and that's it. It'll just sit there at the lower frequency. They don't want to do that, but they'll try to get back. Now, how do we control the frequency? And this is interesting here. You remember down here, this is to just join here, and what we're going to do now is we're going to measure the frequency. And then we're going to have a controller that sends a signal to each governor. And the way that works, this input is, remember over here we used to just have a triangle that said this was a fixed point, and this lever went up and down. Now we're going to move this up and down, and so we're going to move. We have two parts that can move here, and I can actually change this up and down, and thereby I can get the steady state position to go where I want it to as far as the frequency or the valve position itself. So that corresponds to moving the characteristic this way. That corresponds to moving characteristic this way. So what I want to do now is I want to say, okay, look, I got a frequency drop, and I'll just say, so the frequency dropped to here, and the generation went over here. Now what I'd like is that much generation in here on this line, but I'd like to get the frequency back to 60. So I move this characteristic over, and now I'm getting the correct generation. I got more load, but I've raised the frequency back to 60 hertz. And that requires some sort of central device. And it turns out that each power plant has some sort of frequency standard device, but it's not the overarching device controlling frequency. That has to occur at the central location, measuring frequency against a standard. And what they do is they literally receive the signal from NIST, and that signal becomes part of their, that's an input to their control system that says, here is your standard time, your standard frequency signal, measure against that. And they all get the same signal, and that signal is extremely accurate. So, power output as a function of frequency, they call that the speed changers. It's set to give rated speed at rated output. So this is rated output simply means that this is P max over here, and speed changer set to give rated speed at 20%. So this thing pretends that this is P min over here of 0, but the truth is it's not going to be 0. But here it is, it's 20% of the max. And probably you don't let the thing operate much below 20% anyway. So I should simply say that's the P min. Generators do not operate down to 0. They do not operate at a power output less than, let's say, 20. That's a reasonable assumption. They operate and they can't operate above 100. What limits the power output of the generator? Well, the capacity of the generator to handle current at its rated voltage, that will determine how much power output. And so will the fuel handling equipment, the boiler, and the steam turbine. They're all designed to operate up to a certain max, and beyond that you're not. And so everything is designed around that design point for so much power output. Okay, and so I can move this characteristic, okay, with my pen. I can move it back and forth. And here I would keep the standard frequency, or this is percent of rated speed, 100%. Well, let's say for 60 hertz, depending if it's a two-pole generator. Then you can go back and you can say, well, let's see, how many RPM does that come out to be? If it's a 24-pole generator like a hydro system, well, how much? What's that one out? So anyway, this is 60 hertz here, and then if I move this over, I get more power out at the same frequency. Okay, so that's called the speed changer. The frequency reaches steady state at a value causes the sum of the online generator output to be equal to the system load. That's in there, and this is kind of goes without saying here. So if a load is 367, then the speed changers must increase by 7, and we talked about that. They move. They actually move over. You can't see it here with that little bit. So load as a function of frequency. There is an effect on most loads where if I reduce the frequency of the load, the load will actually go down. So for a lower frequency, okay, here's low frequency. I don't know, 59.95, whatever. Then the load, you notice, came down and it went back. All right. Whereas a generator up here came down and the generator went up. So loads have a negative characteristic due to the fact that you have motors, and the motors produce draw less power as the frequency changes. Incidentally, One of the things about doing power, producing power from something like a solar array, okay, a large solar array. You turn it on, and you have an inverter there that converts DC to AC. But if the frequency of the system changes, that's not going to change the power output. See, so a solar array, a PV, would have a characteristic like this. Do anything you want with the frequency, the power output is the same. That's whatever amount of sunlight's hitting the solar array. And I didn't draw that perfectly. I meant to draw this vertically. So this is supposed to be 90 degrees here. There is some work going on now. Dr. Sairaj Dople at our department is working on this. To put this kind of a characteristic into the inverter that's used for solar panels, so that as the power system itself, the frequency drops, okay, then there will be a droop characteristic in that inverter, and it will push more power into the network. Now, you can say, well, wait a minute, that means I'm not generating everything I could from the solar. If it's going to help stabilize frequency and participate in frequency control, then it has to accept the fact that the solar cell does not produce maximum all the time. Okay, but that's the disadvantage. But you can do that. You can bend this green characteristic so that it looks like this one. It can go from this to this by internal feedback inside the inverter. The delta P over delta F is 1 over R. That's the droop characteristic for a generator. For a load, they call delta P over delta F. Same definition, but in this case, the delta P is negative and the delta F is negative. So this comes out positive, where this is considered the delta P for a generator, the delta P is up, the delta F is down. So that's a negative number. So this has to be considered negative. This is called D, and it stands for load damping characteristic. And he then talks about the load frequency characteristic in this slide. Here's again, without the color on here, here's frequency. Notice the scale here. Here's 60, right here where my finger is, going up at the most to 60.04 and down here to 59.8. And so you're seeing different oscillations and generators going up and down like this. You never get the frequency to be one absolutely still, flat thing, because load is always changing and going up and down. He's got a nice little summary at the end. Primary control, the governor. Secondary or supplementary controls, the AGC control response. And it talks about the different inputs and outputs. That's a very nice practical summary that Bob Green did. And if I can get that spreadsheet from him, I think he probably still has it. He gave it to me once, and in my travels here, I seem to have lost it over the years. These are some slides from the lecture, and this is a typical control system type diagram of here's a prime mover with a steam valve and a shaft, and you're measuring omega, and then you have some sort of reference, and you get delta omega. And this is the primary control that adjusts the valve. The integration was taken care of by those fly balls rotating around. They would integrate the delta omega. This is delta omega here, and so they would integrate that and give you a position. And if you took that delta omega and you multiplied it by the droop characteristic, you could feed that back in, and you could get the delta omega to look different until you were at the load reference set point. And that was that nice little point that they rested it on, the little point in the diagram of the flyball governor. So this is just the same thing boiled down to a set of equations that you can put into a control. And those of you that have had our 4721 course know that we have a model of an AGC system with MATLAB's ability to model dynamic systems, Simulink. So here's frequency, and this is it shows you three different droop characteristics. This is interesting. If you have base, what's this? This is the flow. This is the DC power flow model, and we have phase angle difference gives us the tie flow. If the phase angles are changing with respect to time, so we put delta phase angle in there, that I'll have the change in tie flow as the difference in the delta, like this. And if I integrate both sides, okay, if I integrate omega, I'll get phase angle. And so now I've got my control system has omega in it. I put a 1 over S to integrate, and I get the change in tie flow as the integral of the change in omega. So here's this diagram. And everybody that writes a book, we did it in our book, this is where this diagram comes from, does this diagram all the way back to the original book that many of our books are took off from, including the book that I wrote with Wood and Shebley, came from a book by Kirkmeyer, who was an engineer at General Electric for many, many years. He was there when I was working in Schenectady, New York, and he died soon after I came to Minneapolis. A very well-respected engineer in the field. But here is the governor, the prime mover. This represents the 1 over ms is just the mass of the rotating mass, and then there's a little load damping in here. And so if you put power into a rotating man, you go 1 over s, you get a change in speed. And so the change in speed for the area, so this represents a generator up here, okay. And we've got a load down here, and maybe we've got a load with a switch down in here, okay. And then we've got a tie line that goes down here, and we've got another generator, okay. And so this is number 1, and this is number 2. And the fact is that by integrating the difference of delta omega 1 and delta omega 2, there's the 1 over TS. I get the change in flow delta P tie line, okay? And the idea being now that I have two identical, these models here are identical, except for maybe some of the parameter values, but they're identical models of generators. They each have a load reference point, and here's this little delta PF, which P load, which is this change of this switch here. So I get delta PL up here, and the delta omega comes out. Here's the slope or the droop characteristic for generator 1, and here's the droop characteristic for 2. The load reference set point comes from AGC in the control system, and it communicates this load reference set point here. Okay, and that's in the one that we had that we used in our course, the undergraduate course. You can change the load, and you can watch the frequency change in each area. You can watch the tie line change. One of the important things about this model, one of the important things is the following. And before we go too far into this, in an interconnected system, I like to draw them as big circles like this, and there's a tie line between them, and I have loads and generators in both areas. So I have generators over here, and I always like to say, well, let's use some very simple examples. So this will be Minnesota, and this will be Wisconsin. Okay, the thing you want to notice is that if I have a sudden load increase in a load over here, or I lose a generator over here, the frequency is the same everywhere. Frequency is the same everywhere. But if I have a load increase in Minnesota, the frequency goes where? Down. Frequency goes down, and it's the responsibility of Minnesota generation to increase. Not the generators in Wisconsin. However, suppose this load suddenly doubles and the frequency starts to go down. If the frequency is the same everywhere, there's no F1 and there's no F2. So there's no F sub Minnesota and there's no F Wisconsin. It's just frequency everywhere. Well, the speed governors on these generators and these are all going to respond to the drop in frequency, and they're all going to. So let's say that suddenly this one increased. So I had a big delta P load over here. Okay, a big delta P load. Then this guy is going to start to go up. This guy is going to start to go up. We'll put a little arrow like that. So is this one. Well, why should the generators in Wisconsin go up if the load increase was over here? Well, the truth is, what the great advantage to this AC system is that everybody that's interconnected participates in keeping the frequency near 60 hertz. So we get a big load increase. All the generators everywhere. If we have a big load increase in Minnesota, indeed, every generator in the United States east of a line that's approximately drawn north and south from the Rocky Mountains to the east to the Atlantic Ocean. Other than Texas, it would also include a good bit of Canada. And all the generators there would participate and start to go up a little bit. Well, that means they don't have to go up very much to make up for this load change. They don't have to make up very much for that load change. Now, what should happen eventually, and that's where the AGC systems come, is that this one says, your job is done, thank you very much, come back down. Your job is done, come back down. So now he's going to come back down, And these guys should keep going up here until they level off, until the new level completely supplies the P load. These guys have gone back to their pre-event loads generator output. So these would go up and then back down. These would go up and then continue up. These generators pick up the load increase. These generators pick up a little while and they go back. But they all help with the frequency control. We have some little equations like this, and there's a, you know, we said that the change in load. Okay, let's say I have two generators in area 1 and 2 generators in area 2. So the change in load will equal the delta P. Let's say this is area 1 1 plus delta P 1 2. So this is area 1, and then I have plus delta P 2 1 and delta P 2 2. So this isn't a fraction. This is just a continuation here. So I have two areas like this, delta P11 and delta P12. There's two generators there, and here's the other ones, delta P21, delta P22. That's the fourth generator. But delta P, okay, delta P is always equal to delta, put it down as omega, divided by R, right? Times R. So the delta P, we can say that the delta P load is delta omega over R11 plus delta omega over R12 plus delta omega over R13 plus delta omega over R1. This is 2 1 and 2 2. Okay, there's my four generators. But delta omega is the same number. So this is just equal to delta omega times 1 over R11, 1, can you still see it there, 1 over R12, etc., R21 plus 1 over R22. That's delta PL. Well, I know that these R1s, I know all of these numbers. And I know how much the load changed, so I can go back, I can tell you how much the frequency will change on the system. Okay? And that's a typical quick exam or homework problem. And we're going to talk about the fact that if I have generators in two different areas and I have a tie line, I want to control the tie line flow so that after a load event, frequency goes back to 60 and tie flow goes back to the original flow on the tie flow. Here's P tie. That goes back to the original, and the frequency goes back. And to do that, we have two inputs. So there's an AGC here, AGC1, and here's AGC2. He is measuring delta omega at let's say a common bus, but we know that's the same everywhere. So he's measuring delta omega. It's the same frequency everywhere. And then there's a measurement. Remember our state estimator? We had a measure. So I'll put a measurement, a diamond like this, and that's measuring P tie. And we take that measurement and we give that to him, and we give that to him. So they both know how much the flow is deviating on the tie, and we know what the frequency deviation is across the system. And then this is in the lecture notes. There's a thing that says if and so by combining those two together, I can tell which AGC should be worried about having to change its generation. And to do that, they very cleverly came up with a system called ACE, which takes the negative of the delta and the net interchange. This is the flow here, tie flow. And the delta is the difference between scheduled value and the actual measured value. And this is our delta omega, and this is just a constant. Sorry, that's a constant called bias. And ACE, area control error, is still used. It is still used. It is still the best way to do this. And you can see on this diagram of how we took the delta tie flow and we took the bias times delta omega and we combined it. We got ACE. And that was the system that we used to drive this. But these two, if the frequency goes one way and the tie flow goes another, for example, if the frequency go, let's say they go in the same direction, they're both negative, well then it says that there's been a load increase on area 1, and we know there's no load increase on 2. If they're both positive, then it's just the opposite. The load increase was on 2. If one was negative and one was positive, okay, then we know that the load went up in L2. Remember, up here the load went up or down on area 1. Nothing happened in area 2. When they're opposite down here, it was all in L2. So this signal will be 0 for one of the control areas and non-zero for the other, and it tells which of the control areas ought to do this. This is a very crude diagram. Here's frequency, standard frequencies. We get delta frequency times bias. So this thing here is bias times delta F. Here's all the tie flows measured, and then there's a scheduled net interchange, and that gives me an ACE signal. And then this is the AGC that allocates right down to the generators themselves. And if you remember way back, we talked about something called a participation factor, and that's this factor here that allocates the ACE to each generator, and there's an individual control loop that says, you go to this point, and it sends that to its speed governor. AGC itself has a lot of features. These are some of the features that you would get: assist action, move more units to speed control, filter the ACE. They don't want the system to chase a signal that's going to come back. So we'd like to know, is the ACE the ACE is a signal that's jumping around like this, and if it's just oscillating, set your generation to operate along the average, but you can filter it to try to get the oscillating parts of it out of there. If there's a telemetry failure, then you want to turn part of the control system off, not the whole thing, but you want to turn it off, so that the telemetry failure says, I'm not getting through to one of the generators. Well, then don't try to keep raising it up, because it's not going to get the signal. Okay. Unit control. Is the generator not following the actions of the control system? That's very important. If it's not, you probably want to get an alarm out to the power plant. There's always people in a control room at a power plant. we'd like to be able to have ramp control where we set the generator and we say, I want the generator to increase by let's say 5% every hour or something like that, and I can ramp the output up at a certain rate. Rate limiting, I keep the unit from ramping up and down too fast within rates at the same time, and so forth. There's lots of control aspects like that. When I was in graduate school, AGC was undergoing a lot of attention from control theorists. Control theory is a separate branch of not just electrical engineering. At Minnesota, and I'm sure at many other schools, control theory. There's groups of control theorists in mechanical engineering and maybe other areas. The control theorists had come up with something called optimal control, and in the 1960s, the 1970s, that's all they wanted to talk about. And they said, we can do a better job if we apply optimal control to AGC. Lots of excitement, lots of debating, lots of looking at the problem. And then it just died down. Other things like state estimation and optimal power flow became much more technically interesting, and the optimal control theorists kind of walked away from it. The powers, they had other problems to solve, and I don't want to take away from, but the power system control is it doesn't mean that it hasn't changed, but it hasn't changed that much. It is all digital, and it is very smooth. Every manufacturer that makes an AGC computer system can claim that theirs is the smoothest, most whatever control, and they can do a very smooth job. But I don't see any papers in the last 25 years talking about optimal control. Okay, that is AGC at 80 miles an hour. You've gone through the whole thing. I will get these notes to you. You're only going to get 2 pages of these plus my video, and that will be on the web page. One thing else, and I will be sending you all an email. I want you to note that the schedule changed, and I did put a new schedule on the web page. The main Google Drive web page. There's a new schedule with a 2 at, so it's called Schedule New with the number 2. It just took account of the fact that we didn't do the AGC last Tuesday. We did it today, and so everything moved ahead by 1 day. Okay. Very good. We will see you all next week on Tuesday. Your homework 7. Let's put this on here so everybody gets a chance to see this. Homework 7 due April 7th. Homework 8 we'll have that due April 14th. Is that the date for next Friday? It should be 7. Yeah, is the 14th. Okay, and I sent an email out. I had to correct one of the programs yesterday, so you got that email. Okay, and as we do every week, we say good night, and